Hi everybody, in the last couple of videos we've been talking about the one-way analysis of variance, or ANOVA. We talked about the assumptions of the test in the last video. We also talked about the hypotheses related to this test. Now in this video we're going to introduce the equation. We're going to take a close look at the equation and understand what it does. Then we're also going to show you what the statistic that you would arrive at means. We're going to start to get a good understanding of that by looking at the F distribution and then how we make a decision as to whether or not this F statistic that we've obtained is statistically significant or not. So we'll get a basic understanding here. Then in the next video, we're going to actually calculate one, and you can see how this goes step by step. Okay, so very similar to our T equation, the F equation, or the F statistic, is basically a readout of this. It's the variation that is due to the group membership and the proportion of that variation of the group membership to the variation that just exists within the sample anyway. In other words, it's in the numerator, it's how different the groups were on average from each other, the independent variable. And in the denominator, it's how different the people were from each other who were within the groups, regardless of their group membership, essentially. It's a little more complicated than that, but that's the basic idea there. So as you can imagine, if the group membership variation is significant, in other words, it's relatively large compared to just how different people were anyway, just like the t-test, that suggests that there was some influence of the group membership on our dependent variable. And if there was some influence, then we can now start to say it seems to have affected their dependent variable, right? It seems to have had some kind of impact, and therefore it's interesting to us as researchers and as scientists. We now want to assess the relationship even further. So basically all we're doing here is if the amount of variance that is found in the numerator for the F equation is sufficiently large in comparison to the amount of variance in the denominator, then we can say we have a statistically significant F value. Okay, now let's take a closer look at the actual F equation to see how we would actually calculate an F value using some real data, but we'll use the real data in another video. Okay, so here's our actual F equation, and I know this looks like a lot. This is a lot of stuff going on, but don't worry, it's actually not nearly as bad as you might think. First of all, as you can see here, there are many repeated elements. In fact, you've got this thing that is repeated both here, or it's repeated right here. You've also got this thing that is repeated here and here, for example. And so we don't have to calculate a billion things. We're going to calculate a couple of things, and then we just plug them right into the equation where they go. So it's just a little more complicated than any of the other equations we've been doing, but nothing we can't handle. Now, you also will hopefully notice that all of these symbols look very familiar. If you've been following these videos at all, we've done all of this. Sigma x sub 1, very similar to our previous groups, our independent samples, t-test for example, that's the sum of everybody from group 1, right? The sum of all of the x scores from group 1. The scores, everything looks familiar. Now, one thing that's maybe a little bit different is we haven't seen the letter K before. In this case, K represents the number of groups that you have, the number of groups that you're comparing. Okay. Now, in this particular equation, as you may guess, there are 3 groups because, as you can see, we have only all of the scores from group 1, the scores from group 2, and this is the scores from group 3. So I don't have any more than 3 groups in this particular equation. Now, it's easy, of course, to add groups. We can do that in just a second. I'll show you what that would look like. If I were to add a single group, of course, I would need to add a few elements here. Now, the only other thing also that shouldn't be confusing, but where it says the subscript here of total, that means regardless of the group membership, just add every single squared x score right here, for example. And then here it says sigma x subtotal, meaning just add up all of the x values, right? Every single one of them to get the grand total. Okay, so if I had 4 groups then, what I would have to do is add in enough elements so that I'm accounting for the 4th group as well. So as you can see here, I've simply added in right there this guy that accounts for all of the scores in group 4. And again, this is the number of people, or observations if it's not people, the number of observations for the variable, the dependent variable in group 4. And then that same thing appears here again. And then of course, K would become 4, obviously, because we have 4 groups. Okay, and now you can expand this. If you have 6 groups, for example, of course, you would add 2 more. You would add one of these for group 5, and then one for group 6, and then the same thing down here, and then K would equal 6, and so on. So nothing too terrible there. Now, All we do to compute this is, of course, as I said, we'll compute the little things in the parentheses, we'll come up with these, and then I don't have to compute it again, I just add it back down here. In fact, as you can see here, we already subtract this guy from that, so I don't need to do that every single time. I can do it once and then just add it into the equation. So it actually doesn't take that much time. It's very similar to the independent samples t-test if you've been following all of these. Now let's better understand what the F statistic will mean. So once we've obtained an F value, what does that actually mean? So you recall with the t-distribution, it was a bell-shaped curve, right? Because the difference between mean 1 and mean 2, or whatever criteria we were using, could either go in the negative direction or the positive direction, and there was really no reason to believe that it was necessarily going to be skewed one way or the other. In fact, there was equal probabilities of either one, essentially. Now, in an F distribution, it's not that way at all. It is specifically positively skewed. And in fact, this is a little bit misleading because the actual shape of the expected theoretical F distribution depends on how many degrees of freedom your test has. But we're just going to use this one as a model for theoretical purposes. It's not an issue, just be aware of that if you're going on to advanced statistics course especially. So let's talk about why it would be positively skewed. Well, first of all, you'll notice here that it can't be lower than 0, right? As you can see here, there's a cutoff. There's a clear cutoff for the F value to be no lower than 0. In fact, that is impossible to obtain an F value that is negative. The reason for that is, of course, because, as you may have noticed in the equation, we square every value, okay? We sum up the values and square them, and then we also square the sum of all of the values as well. And so it's impossible that we end up with some kind of negative number in the numerator. Therefore, every F statistic has to be positive. And therefore, we have no chance whatsoever of obtaining a 0 statistic. Now, what's interesting here also is that if we're thinking back of that numerator to denominator kind of idea, if you have a smaller numerator than the denominator, that's a pretty boring statistic because that means that the group membership didn't really have much of an effect, right? The groups just weren't that different from each other, especially in relation to how much they differed from each other. The people differed from each other generally, that within groups variance. And so if we can't find any differences that are, or at least meaningful differences that are due to that group membership, it's a really boring F statistic. It means that our independent variable didn't have any influence on our dependent variable. And so we're likely to find an F value that's lower than 1 because the ratio of the numerator to the denominator would be lower than 1. Now, what's important then, yes, exactly, and this is why. So you would expect it kind of, if they were equal variances, now you might find a value of 1, but even that isn't quite meaningful enough. Now let's talk about that. So of course, any value lower than 1, any F statistic lower than 1 is just not really interesting. It's a pretty boring F value, okay? Because again, that means that we just didn't have an influence over independent variable on our dependent variable, at least not enough that we would start to throw pizza parties and get interested in this kind of stuff. Okay, and that's exactly why. So anything lower than 1 is going to be very uninteresting. Now, anything a little bit bigger than 1 is a little more interesting, but it also just isn't enough that we can start to say that we really found something there, right? It's got to be, if it's bigger than 1, that means we're getting closer to something interesting because we're starting to see some kind of influence of the independent variable on the dependent variable. In other words, the group members seem to be a little more different from each other based on their means, but it's just not quite to the point where we can say we would probably start seeing this pattern consistently, or we found a big enough effect of our independent variable on our dependent variable that we can start to say there really is some kind of real world effect on them. So then, of course, when we find an F value that is quite a bit larger than 1, now we can start to say this is a pretty clear effect of our independent variable on our dependent variable. In other words, that's just saying that we seem to have found enough differences among our group means compared to just how different people were from each other generally, how much variation there already was in the sample, that we can start to attribute the broad mean differences to their group membership, as opposed to just some kind of accident or some kind of anomaly, some kind of statistical anomaly. So that precise threshold of where we can start to say that, of course, differs depending on how many degrees of freedom we have for our particular test. And I'll show you how to calculate all that as we go through an example. But that is where we find our F critical value. It'll tell us that minimum threshold for when we can say that we found a statistically significant F value. Okay, so we'll see all this when we go over an example in the next video. quick summary of what we talked about today is a one-way ANOVA, of course, uses exactly the same concepts as a t-test. It just expands them to use two or more groups. Now, that's the advantage of an ANOVA. We can use more than just two means. We can now use 3, 4, 7. It doesn't exactly matter. The numerator looks at those differences that are just due to the group membership. And then the denominator, of course, is the variation that is accounted for, not accounted for by the group membership, but is due to just the differences of the individuals who were measured in there, whether it's people or something else. Okay, and then once we get the ratio of that, that's the F statistic. When we get the ratio of the difference between the numerator and the denominator, that is our F statistic. If it's relatively large, if it's sufficiently large, we can reject our null hypothesis. We can say there was an influence of our independent variable on the dependent variable, and it was not likely to have been just an anomaly. Okay, statistically significant. Now we'll calculate an actual F statistic in the next video, and I will see you then. Then we'll work on interpretation. All right, thanks.